Okay, so in this video, we're going to look at how we work problems using the concepts from the last video on horizontal projectile motion. So, working problems involving projectile motion. A fairly typical problem like this would be a ball rolling off of a table, and the question would be how far away from the table will the ball hit the ground? So if you remember from our introduction to projectile motion, we talked about how when you look at projectile motion and it's curving down, we have to consider what it's doing horizontally and and separate that from what it's doing vertically. So in this case, we will identify this 10 meters per second as a horizontal velocity, and that's going to stay the same the entire time. So this horizontal part of the velocity will stay the same the entire time. Looking at the problem, we're told that this table is 1.2 meters high, but this is a vertical thing. So I'll call that delta x v for vertical and say this is 1.2 meters. We're asked to solve a distance away from the table, and that's a horizontal distance. So as usual, diagrams really help us. And that's what we want to solve for. And then there's other stuff that's not staying in the problem that we know and we want to put on our diagram. So for instance, we know that our acceleration is vertical and it's going to be 9.81 meters per second squared. We're assuming we're on the Earth, kind of around sea level. So 9.81 meters per second squared. Just as an aside, when we do this, not only do we have to choose a positive direction horizontally, but we also have to choose a positive direction vertically. So we kind of like need a two-dimensional coordinate system. So that's what we know. And so as I'm approaching this problem, I have a few ideas in mind that I'm going to keep in mind as I do this. First of all, this horizontal velocity is constant. Okay, so this component of the velocity is not going to change the entire time it's in the air. So therefore, I can get this horizontal distance by simply taking the horizontal velocity times the time that it's in the air for. So when we solve a problem like this, the first thing that we look for and we need to solve for is this time in the air. The other idea I have is that this vertical component of velocity, so remember, that's where, if it was right here, and we look at the velocity, which would be down this way, it's going to have let me make that a bit longer to make my point. The velocity itself, we go down this way, but it's going to have this horizontal component, and it's going to have this vertical component that's changing with time. Although this is what we would actually observe, we can think of it as having two directions to it. So this component right here changes, which means that it accelerates. Okay, we have acceleration in the vertical direction. Therefore, we have to use kinematics. Whenever we have a change in velocity with time, we can't just say distance is equal to velocity times time because velocity is not the same. So we have to use kinematics. And then the final idea that I'm going to have here is, due to this, I'm going to solve for the time in the air using this vertical height, and then I'm going to use this to plug into delta xh is equal to vh times time in the air. Okay, so this is my thought process here. And as I said, the first thing I need to do is find out how long it's in the air for. So I'm going to use height, and I'm going to say, okay, my delta xv is 1.2 meters. And again, I cannot emphasize this enough. You have to be very strict when you work these problems. You never, ever, ever, ever want to plug a vertical variable into a horizontal equation, and you never want to plug in a horizontal variable into a vertical equation, in other words, kinematics. Okay, so whenever we use kinematics, we ought to make sure that we're always using vertical stuff. So we have a vertical displacement, Although it's not stated, I know because it flies off the table horizontally that my initial vertical velocity is 0 meters per second. This little knot here means initial. I don't know the time in the air. Okay, so that's going to be my known. I know my vertical acceleration is 9.81 meters per second squared. So I know these, so I'm going to look for a kinematic that will allow me to solve for this time in the air using these variables that I know. And so you look a little bit and you'll see this one, delta xv is equal to v naught times t in the air plus 1/2 a v t in the air squared. This is just the kinematic equation. I put these little subscripts on it just to keep straight in my mind and remind myself which variables I have to use, but this is just the kinematic equation that we've used before. And again, we can always use kinematics as long as we're solving for vertical things. We can use it to solve for vertical distance or the vertical component of the velocity or the time in the air. So as I said, it has no initial vertical velocity, so that's 0. That's going to drop out, and this will become delta xv is equal to 1/2 a times time in the air squared. I'm going to do some algebra here, so I'm going to multiply both sides by 2. I know how much you guys love when I work in variables, but it's so much nicer than having to plug numbers in right away. I'm going to solve for the time in the air. So time in the air squared is going to be 2 delta xv divided by av, and then take the square root of this. And what we get is an equation that tells us how long it's going to be in the air before it hits the floor. So 2 times 1.2 meters divided by 9.81 meters per second squared. Take the square root. And so from this, we can see that it's going to be in the air for, I'm going to use some extra I'm going to carry some extra digits here, 0.495 seconds. Okay. So this reiterates the point. It doesn't matter whether I drop that ball straight down or whether it flies off the table, it's going to spend the same amount of time in the air. What it's doing horizontally doesn't affect what it's doing vertically at all. So 0.595 seconds. And now I have what I need to solve for my horizontal distance. So I say horizontal distance is going to be equal to the horizontal velocity times the time that's in the air for. From the problem, we were given our horizontal velocity is 10 meters per second. And again, that's not changing, so I don't need to use kinematics. And the time in the air, we just saw 4.495 seconds. So this is going to be 4.95 meters to 2 sig figs. It'll be 5.0 meters. And so from this, we see that the ball is going to hit the ground 5 meters from the edge of the table. And that, guys, is how you solve a projectile motion problem. So I hope you guys took good notes. If any part of this was confusing, I suggest you guys write down your questions and then bring them to class tomorrow. We will practice solving these types of problems in class, and you will have time to get any clarifications you need then.